Hey, good morning, everybody. Good morning, Mr. Burkett. Good morning, Wood. Good morning, classes. Hey, good morning, Calvin. Come back up here.
What?
Look, we've got our pajamas on because it's Monday. It's pajama day in our virtual spirit week. All right, go build some Legos, bud.
Okay.
Anyway, welcome back. We're going to start with a little warm-up to refresh on the things that we've been working on. So first, we're going to work on factoring. We might remember the first thing we do when we factor is we look for a greatest common factor. So this one I can take out a 2. And then we need to show what remains. That'll get us back to our original trinomial, which will be x squared minus 2x minus 15. And then because we still have a quadratic, we can put that in the box and see if we can factor that. We go first term, first box, last term, last box. We must add to negative 2x. We must multiply to x squared times negative 15, which is negative 15x squared. And let's see, negative 2, negative 15, that's going to be negative 5x and a positive 3x. And then finally, to finish factoring, we're going to take out my greatest common factor from the top row, which is x, and then figure out what we need to multiply to get all of the other terms. And we end up with x minus 3 times x minus 5. But we're not going to forget the GCF. We're going to take that 2 that we took out at the very start, and we're going to throw that right in front. So the factors of number 1 are 2 times x minus 3 times x minus 5. Number 2 is one of our difference of 2 squares. We might recognize that the front term is a perfect square. Our constant term is also a perfect square, and we have a difference in the middle. So we can break that up into our 2 binomials. Square root of x squared is x. Square root of 49 is 7. And then in order to get a negative, we need to have a positive times a negative. And again, if that made no sense, just go back and rewrite it as x squared plus 0x minus 49. Throw it in the box, and you'll end up getting x plus 7 times x minus 7. All right, a couple weeks ago, we did solve using square roots, and that is where we ended up taking the square root of both sides. And this problem is set up nicely for that because we have the parentheses squared equals. And so to undo the squared, we're going to take the square root. That makes the squared and the square root cancel out. X plus 5 equals. We take the square root of 13. However, 13 is a prime number, so it is not going to be able to be simplified. So I'm going to put plus or minus square root 13. And then our final step, we want to get x by itself, so we're going to subtract 5. And we get x equals negative 5 plus or minus square root 13. And at that point, since this is something that we can't simplify, we're fine just writing it out as 1 solution, but it's actually 2, right? Because we have negative 5 plus square root 13, and then negative 5 minus square root 13. One more of these, because this is actually going to be a big part of what we're doing today in our new lesson. But we're going to start by getting rid of that 3 out front by dividing, which leaves us with x minus 2 squared equals 7. To undo the squared, we take the square root. Once again, we have a prime number, so we can't use the factor tree to find any pairs. We're just going to leave it as plus or minus square root 7. And then finally, we're going to add 2 to both sides. And that gives us x equals 2 plus or minus square root 7. So hopefully you remember that from the previous lessons. How do I change the page? Where did that go? Well, I'll be right back. That was weird. There it is. I found it. All right. Sorry for that delay. I'm back. Solved by factoring, the only difference between factoring and solved by factoring was we now have the equal sign and we're going to actually solve for x. We did a couple last week where there was no c value, which means to factor that we will take out the GCF. So the greatest common factor is x, which leaves us with x plus 9, and then the problem is equal to 0. Once we factored it, we set each factor equal to 0. So I'm going to do x equals 0. There's one of our solutions. And then we'll do x plus 9 equals 0. Solve it. And our second solution is x equals negative 9. All right, so again, quadratics can have as many as 2 solutions. Number 2, oh man, this looks way too scary, right? Look at all those fractions. That's right, to do this problem, we can just multiply by the common denominator of all of the terms, which the common denominator would be 8. So I'm going to multiply everything by 8. So 8 times 1/8, the h just cross out. 8 times 3/4, you actually multiply the 8 times 3, which is 24. Divide that by 4, which is 6. So you get plus 6x. And then 8 times 5 is 40. When we solve by factoring, though, we don't want 40 over here. We want this to be 0, right? Remember that from last week? So I'm going to subtract 40 on both sides. X squared plus 6x minus 40 equals 0. I look for a GCF. It does not have one, so I go straight to the box. Sorry, it's such a little box here, but that's all right. First term, first box. Last term, last box. We need to add to positive 6, and we need to multiply to a negative 40x squared. So multiplies to negative 40, adds to 6. That's going to be positive 10x and negative 4x. Take out my greatest common factor from that top row, which will be x. And then this will be x plus 10 and x minus 4. So I write out both my factors. X minus 4 equals... Sorry, let me try that again. We're going to skip this problem so I have enough space to do the problem we're working on. Our factors are x minus 4, x plus 10, and we need to set the problem equal to 0. So we're almost done, right? We factored it, we set it equal to 0. Now to solve it, we set each factor equal to 0. So x minus 4 equals 0. X plus 10 equals 0, and we solve each one. And we get x equals 4. And x equals negative 10. So again, 2 solutions. This is just to kind of refresh us on what we've done in the previous weeks, because we're still going to have you do these problems. But moving on to what's going to lead us into a new idea for today. So this first problem, it has part A and part B, and it asked me to factor each function and determine the zeros if possible. So determining the zeros just means I'm going to plug in 0 for my f of x or for my y, which if you think about a graph, if your y value is 0, that means you're on the x-axis. So these are also going to be my x-intercepts. So I'm going to do 0 equals x squared plus 5x plus 4. I'm going to solve it by factoring. So let's see, using our box. First term, first box. Last term, last box. Add to the middle. Multiply to the diagonal. All right, multiplies to 4, adds to 5. Not 2 and 2, because that won't add to 5. It's going to be 4x and 1x. GCF is x. Go around the outside. Hopefully at this point I can go a little faster and you guys can still follow. But we end up getting factors of x plus 1 and x plus 4. Set that equal to 0. And then to get my solutions, or my zeros, or my x-intercepts, or my roots, right, all of them being the same thing, I'm going to set each factor equal to 0. Subtract 1 on both sides, and x equals negative 1. Set the second factor equal to 0. subtract 4 on both sides, and x equals negative 4. So yeah, no problem, right? That worked. I was able to solve it by factoring, got my two solutions, which are my two zeros. But then I come over to this second problem, problem B. And I plug in my 0. There's no GCF, so I go straight to my box. X squared, positive 2. Need to add to the middle. And then needs to multiply to 2x squared. Needs to multiply to positive 2 and add to negative 4. Dun, dun, dun. Well, you might have figured out by now the only ways to multiply to 2 are 1 times 2 and negative 1 times negative 2. And do either of those add to negative 4? They don't. Oh no, this problem cannot be factored. So, problem 2 says, were you able to determine the zeros of each function by factoring? The answer is, for A, that's that problem right there, yes. But what about for B? Were we able to factor it? We were not. So for B, no, not factorable. So that's right. A lot of the problems we do can be factored, but there are also a lot of problems that cannot be factored. So if we go ahead to the next question, or the next slide, this is actually the graph of the problem that we couldn't factor. And we are hopefully starting to pick up that the solutions are also our x-intercepts. So if I look at this problem, and I look at the graph, does this function have zeros? Does it have x-intercepts? Well, yes. How do I know? Look at the graph. Right? If I look at the graph, there's a 0 right there. There's a 0 right there. So I know that this problem that we were trying to factor, it does have solutions. But by factoring, we weren't able to do it. If we look closely at the zeros, and I get you probably can't see this very well, but this is quite a bit different because these zeros appear to be decimals. Like on problem A, our zeros were negative 1 and negative 4, which means if we were to graph that problem, we would cross right here at negative 1 and right here at negative 4, right? That's nice and easy to see. But on the second problem, the two intercepts are in between some numbers. So we don't know exactly what numbers those are on. So they are decimals. Interesting. So we couldn't use the square root method on it. We can't factor it because we tried factoring and it doesn't factor. So what are we going to do? You guessed it, we are going to find another method. Exciting. So today's new method, it's going to be called completing the square. All right, so let's talk about completing the square. The first thing in order to be able to complete the square is we need to be able to solve problems where we have a perfect square, which we've already done. Right, we did this problem on the warm-up today. In order to solve, right, this is a perfect square because x plus 5 squared means, if we put it in the box, we have x plus 5 and x plus 5. And the definition of a square is that both sides have the same length. So this square, x plus 5, x plus 5. Right, most of the problems we've been doing are not perfect squares, they're actually rectangular boxes. But this problem is actually a perfect square. So once we have a perfect square, we know we can take the square root, put our plus or minus, and then if we have something to undo, right, we'll undo that 5 by subtracting 5, and we end up getting that the two solutions, or the two x-intercepts, are located at negative 5 plus square root 13, and the other one is at negative 5 minus square root 13. So we do still have two solutions. So going back to the problem that we were trying to factor that we couldn't factor, the one that we looked at on the last page, how can we turn this into a perfect square? Well, let me tell you. The first thing we're going to do is we're going to take the c value and we're going to actually get rid of it. I'm going to move it over to this other side. Right, so I'm going to subtract 2 from both sides. That'll give me x squared minus 4x plus a new number that we're about to find equals negative 2. So again, first step, move the c to the other side. Now we're going to take these two terms and we're going to put them in the box, and we're going to figure out what needs to be our c value in order to make this factor into a perfect square. So again, first term, we always know that goes first box. If it's x squared, I already know it's going to be x and x, right? We're pretty smart, we figured that out. But then I also know that these two boxes here have to add to negative 4x. Well, if I want it to be a perfect square, I need to have the same numbers on the outside of the box. So if we're going to add to a negative 4x, we're just going to split that in half. So half of negative 4 is negative 2. So I'm going to put a negative 2x and a negative 2x. Because now that gives me x times negative 2 and x times negative 2. So this is the important part. We have created a perfect square. This box has the same binomial on top as it has on the side. They are exactly the same. It is a square. But we have not filled in this last box. So if we look at the problem, it should become pretty clear what number has to go there, because it has to be negative 2 times negative 2. And if we multiply those together, this is a positive 4. Now, in order to make this factor into this perfect square, what has to be our c value? It has to be 4. So I'm going to add positive 4 to my trinomial. Now, what we know about math is if we add something to one side of the problem, what do we have to do to the other? We have to add it over here as well, right? So if I'm going to add in this 4, I must also add that same 4 to the other side. So now we end up with this problem on the left, which if we factor it, we know what it factors to because we just used our box. It factors to x minus 2 squared. So again, this problem, once we put the 4 in, it factors using the box to x minus 2 squared. The right side of the problem, we add negative 2, we add 4, which gives us positive 2. So that step we did, I get right now one example, you might be super confused, and that's fine. We're going to do a bunch more examples. You'll start to get the hang of it. But hopefully you notice at this point, we have gotten back to a problem that is just like the problems we did a week or two ago with the solve using the square roots. So at this point, we can start using our square root method. We're going to take the square root of both sides. 2 is a prime number, so we're just going to leave that as plus or minus square root 2. And then we're going to add the 2 to both sides. And we end up getting x equals 2 plus or minus square root 2. So if we were to plug this in our calculator and turn it into decimals, 2 plus this number and 2 minus this number would be these two decimals right here. So something a little bit less than 1 and something a little bit bigger than 3. But when we're doing these problems, we're just going to leave them as in the exact form. So we're going to leave it as 2 plus or minus square root of 2. So we couldn't factor that problem, but could we still solve it? Yes. Solving by completing the square. All right, so here are the directions. Feel free to, take a screenshot or take a picture of this. I'm not going to read through it because that won't probably help you that much. We're going to see it in action. So to do these steps, the first thing we're going to do is we're going to make sure that our c value is on the other side, which for this problem it is. That is good. I wanted that over here. Then I'm going to rewrite this as x squared plus 8x plus our new c value equals 11 plus our new c value, because whatever we add to one side, we must add it to the other. Then we're going to start filling out our box. First term, first box. Last term, last box, we don't know what that is yet. But we do know that to make a perfect square, we're going to split our middle term in half. So half of 8x is going to be 4x and 4x. So we can go ahead and factor what we have so far. We can take out an x. That has to be x. This has to be plus 4. This has to be plus 4. So we now have a perfect square, right? Same length, same length. That is a square. And then we're going to figure out what our new term has to be right here. So if we have 4 there and 4 there, this has to be 16. So we are finding our new C value. That new C value we're going to plug in. But if we add it to the left side, we have to add it to the right side. And this will now factor to, this side here, factors to x plus 4 squared. Right? Because if we have 16 here, we know that if we use the box, we get x plus 4 and x plus 4. So x plus 4 squared. The right side, 27. All right, I'm going to move this on down here so I have room to show my work. At this point, we've gotten to the square root method. So we complete the square, and then once we've completed it, we can use our square root method. X plus 4 equals. Now the square root of 27 is not a prime number, so we can use our factor tree. 3 times 9, 3 times 3, and we end up with 3 3s. For every pair, we can cross it out and let it go outside. And then the one left over stays in the radical. And then of course I can't forget my plus minus. And then finally, to get x by itself, we're going to subtract 4 from both sides. And we get x equals negative 4 plus or minus 3 square root 3. Nice. All right, example number 2. This one, we need to move our c to the other side, so I'm going to move it over here, which gives us x squared minus 6x plus our new c value equals, we add 10, right? We need to add 10 to both sides, plus 10, plus 10. So that equals 10 plus whatever our new c value will be. I know first term goes first box. I know we're going to split the middle. So if we split that, we get negative 3x, negative 3x. If I factor around the outside of the box, I know this is x minus 3, minus 3. And what does our new c value have to be? Negative 3 times negative 3, which is 9. So 9 is the number that gets added to both sides of the problem. And by adding that 9 into the problem, we know that this left side will now factor perfectly to x minus 3 squared. Right? X minus 3, x minus 3. And it'll equal 10 plus 9, which is 19. Take the square root. X minus 3 equals plus or minus square root of 19. I knew that square root of 19 didn't break down using the factor tree, so I just went ahead and skipped forward. And then we add 3 to both sides. X equals 3 plus or minus square root 19. Completing the square. All right, just a couple more. So this one, we have the right side equal to a negative. That's fine. We don't have our c value, which is good, right? Because we wanted to move c to the other side. So I can rewrite this as x squared plus 16x plus blank equals negative 44 plus blank, right? And our blank will be whatever our new c value is. First term, first box. Last term, don't know what it is yet. Split the middle so that our 2 leftover boxes add to the 16x. Factor it out. This has to be x plus 8 plus 8. And what is going to be our new c value? You got it, 8 times 8, which is 64. So we're going to add 64 to both sides, which gives me this side, which now factors perfectly to a square, x plus 8 squared. And then the right side, negative 44 plus 64, which is 20. Take the square root of both sides, and you get x plus 8 equals plus or minus. And then the square root of 20, if I do the factor tree, 2 times 10, 2 times 5. We've got a pair of 2's, so the 2's get to leave the house. And then the 5 left over, so the 5 stays inside. And then finally, we're going to move this 8 to the other side. And we've got x equals negative 8 plus or minus 2 root 5. All right. So again, one more example. We want the c to go to the other side. So I'm going to add 10 to both sides. When we do that, we get x squared minus 10x plus our new c value that we're going to find equals 10 plus our new c value that we're going to find. I'm going to put this in the box so I can figure out what c value we need to make it a perfect square. I get x squared. What do we do with the negative 10x? Split it in half. So negative 5x, negative 5x. That allows us to take out x minus 5 as our perfect square. And in order to make this a perfect square, we need negative 5 times negative 5, which is a positive 25. So 25 is that number that's getting added to both sides. This factors into the box we just used, so x minus 5 squared. The right side adds to 35. And then solve it. Square root, square root. Oop, don't need that parentheses. X minus 5 equals plus or minus, and 35 is just 5 times 7, so there are no pairs, so I'm going to leave it as square root 35. Add 5 to both sides, and we have solved it. It is 5 plus or minus square root 35. So if we're trying to solve a problem and it is not factorable, we can use completing the square. Okay, I do want to show you just one example of what happens if a problem was factorable and you complete the square. So for example, if we do x squared plus 8x plus 15, which this one actually does factor. It factors to x plus 3 times x plus 5, and then you set those factors equal to 0 and you get negative 3 and negative 5. So we could solve it that way. But we could also complete the square. If we decided to complete the square, we would move our c value to the other side. We have x squared plus 8x plus our new term equals negative 15 plus our new term. Draw our box. X squared, split the 8x. Take out our common factor. Multiply around the outside. And what number has to get added to both sides? That is right, 4 times 4, which is 16. So we add 16 to both sides. The left side now factors to the perfect square, x plus 4 squared. The right side is now equal to 1. We take the square root, but now what do you notice about the right side? It is a perfect square. So if it is a problem that would have been factorable, it probably means you're going to get a perfect square here, which is kind of interesting. We can now write the left side as x plus 4, and then the right side is plus or minus, and the square root of 1 is 1. No more square root in there. So now we can subtract 4 from both sides. X equals negative 4 plus or minus 1. And since there's no square root anymore, I